Welcome back to Dave's Math from Home. This is part 4 of our video series on section 17.1 vector fields. We were just talking about how to determine whether or not vector fields were parallel is not the right word because none of these things are straight. How to determine whether vector fields are tangent to curves or perpendicular to curves. So we use sort of the implosion vector field with a circular curve to see what that's like. The actual process gets a little messy with things that are perpendicular to the perpendicular to the perpendicular, but it does check out in the end. So now we're going to do something a little more technically challenging. It's the same question with just a more complex vector field and a more complex curve. The vector field isn't much more complex. It's my favorite. This is the toilet flush vector field going in circles. The curve is going to be y equals x squared plus 1. And so this is just a parabola, opens upward, has an intercept of 1. This is not the correct formatting for a curve. So the first step in these problems is always to transform your curve into something that could feasibly be the level curve of a larger potential function. And the level curves always mean a function of x and y equals a constant. So we're going to rearrange this a little bit. I'm going to say y minus x squared equals 1. Now I have a function of x and y is a constant. So now I'm going to say that this function of x and y is my potential function phi. Phi is y minus x squared. And I'm going to take the gradient of that. Del phi equals, derivative with respect to x is negative 2x. Derivative with respect to y is positive 1. This is my gradient. So, to check for tangency, I'm going to see where the gradient is perpendicular to the vector field. So f dot del phi is going to give me 2xy plus x. And I want to set that equal to 0. This now becomes one equation of two variables, and that's going to be difficult to solve. But we have to remember that we're still always on this curve. Like you could say the point 0, 0 solves this, but that doesn't help us because 0, 0 is not on this curve. So that's pretty useless to us. We want to use this as our second equation because all the points we care about are constrained to this curve. So I'm going to just do a simple substitution here. We'll say 2x times y is x squared plus 1 plus x equals 0, which will turn into 2x cubed plus 2x plus x equals 0, or 2x cubed plus 3x equals 0. Now we have an equation of one variable. It's a lot more plausible to solve for that. I'm going to pull an x out. 2x squared plus 3 equals 0. This thing doesn't factor, and in fact it's never ever ever equal to 0. This piece is always, 3 is always positive, 2x squared is always non-negative. So there's no value of x that will make this equal to 0, so we don't care about that. You have x equals 0 here. And if x equals 0, I can look at this function to figure out what y equals. Y should be 1. So at this point right here, I should have tangency with this vector field, which seems plausible. The toilet flush goes this way at that point. So I'm willing to convincingly believe that this is the only point on this parabola that is tangent to the vector field. I can do a slightly more zoomed in version over here. Here's the parabola, here's the vector field. Those are tangent. The gradient is going straight down, or maybe straight up at that point. Straight up. Gradient at this point points straight up. The vector field points straight left. Those things are perpendicular, which means the vector field is tangent to the curve. So there's that, at just this one point. Let's find where it's perpendicular. And for that I'm going to have to erase all of this tangents and stuff. Okay. Tangent was at 0, 1. To find out where it's perpendicular, I need a new vector field n, which is always perpendicular to the gradient. And I do that by switching the order and flipping the sign of one of them. So this one was negative, I'm going to make it positive. This is my vector field n. And for perpendicular, I'm going to take f dot n to get negative y plus 2x squared. I want that to be 0. Again, I'm going to substitute y using that stuff. So negative x squared minus 1 plus 2x squared equals 0. I'm going to move the 1 to the other side. Combine these like terms into x squared equals 1, which will give me x equals plus or minus 1. So, I should have 2 points here. X equals 1, y equals 2, and x equals negative 1, y equals 2. Apparently, I've lost my opportunity to draw this thing big. So, I'm going to clear out this algebra work so I can draw a picture. Do this real smooth. Okay, these are the 2 points in question. 1, 2, negative 1, 2. The toilet flush here should be going this way. Toilet flush here should be going this way. So I'm prepared to believe that this vector field, the toilet flush vector field, is in fact perpendicular to this parabola at these 2 points. 1, 2, negative 1, 2. Because the gradient is pointing, in fact, is this equal to the gradient at that point? So at the point 1, 2, the gradient should be negative 2, 1. And the vector field here would be negative 2, 1. Yeah, okay. So this is in fact equal to the gradient there. Here the gradient probably points up, but the flush points down. So still perpendicular. That is all we need. We don't need the directions to match. We just need the perpendicularity to happen. And we got that. So that's it for vector fields. I hope that that was a entertaining ride for you. The good news is it gets better from here. Following this, we're going to do line integrals, which are one of my favorite parts of Calc 3. I love line integrals. That's where we're going to look at a path through a vector field, and we're going to integrate all of the forces that that vector field applies to an object that is moving across that path. It'll be a real good time, trust me on that one. But for now, I'm going to shut this whole thing down. Do some 17.1 homework.